Here we got another rational expression. Now, whenever you have a rational expression, especially if you have a variable in the denominator, something that restricts our domain, you're going to have to figure out the asymptotes, or what the function cannot equal. So the first thing we do normally is we take the denominator, we set that thing equal to 0. And once we solve this one, we get x equals 2. That's going to be our vertical asymptote. Let's go ahead and start that graph here. So I threw my vertical asymptote on there at x equals 2, and then I look for my horizontal asymptote. Now in this situation, the degree on the top is equal to the degree on the bottom. If you forgot what a degree was or is, all you have to do is look at the exponent, not the exponent, the variable on the top, and find the highest exponent on the variable. Now in this case we only have one x on the numerator, so we only have to worry about this one. And since that's the only one, he has nobody to compare with, the degree of the top is 1 because the exponent on this x is 1. Same with the scenario on the denominator. So what we do is we take the leading coefficients of the top polynomial and the bottom polynomial, and we divide them like so. This becomes our horizontal asymptote. So let's go ahead and draw that on our graph. Alright, now this is calculus, that's right. So let's do our first derivative test right now. In order to do our first derivative test, we must take the derivative of this thing, and because we have a binomial in the denominator, we must do the quotient rule. So let's still go right here. Whoa, slow down here. So the derivative of the top is 3, then we multiply it by the bottom, and then we could do the derivative of the bottom, which is 2, and then we multiply that by the top. Don't forget to square the bottom. I'm not going to square the bottom though. I'm just going to simplify what's going on up top. So let's distribute those guys, and we get this big old polynomial expression up top. And then we simplify it some more. We get negative 16 on top, and on the bottom we have 2x minus 4 raised to the second power. Now what we normally do here is we set it equal to 0. We set the f prime equal to 0. And then we solve. We multiply both sides by the denominator, and lo and behold, our variable goes away, and we're left with an untrue statement which says negative 16 equals 0. If we end up with this, then we know there's no critical points. Alright, well, what about our second derivative test? Come on, our beloved second derivative test. He can't fail us. So let's do it. We have the derivative of the top, which is 0. And then we're supposed to multiply it by the bottom, and I don't really have to do that because it's just going to be multiplying by 0, but I'm trying to be thorough. And then we say minus, oops, I have no more space. Hold on one sec. Now we multiply the top times, the top is negative 16. We're going to multiply it times the derivative of the bottom. Now the bottom has an exponent, so that means chain rule, people. We drop this 2, we're going to multiply that 2 times the 2x minus 4. Then we're going to take 1 away from that 2 so that it's a 1 up top. And then after that, we're going to take the derivative of the inside and multiply that. And then of course, we write the bottom down here and we square that again. So we square that, which actually wouldn't be a 2 anymore, it would be raised to the 4th power. Alright, if we simplify the top, the left side goes away. And let's simplify this side right here. We have, actually let's just multiply those constants together. We have a negative 16, which means a positive 16. Positive 16 times 2 is going to be 32. 32 times 2 is going to be 64. And that's multiplying to 2x minus 4. And I didn't multiply that out for a reason, because I saw something. Right here. We can cross out 2x minus 4 and make this into a 3. So our f double prime is 64 over 2x minus 4 raised to the 3rd power. Okay, now if I set this thing equal to 0, we're going to get the same scenario as we did over here. So it looks like we're not going to have an inflection point, because when we set this equal to 0, we just get 64 equals 0. Inconclusive. Alright, so let's think about this for a second. Let's see, for this graph, we don't have our y-intercept down there, so let's get that guy going here. We're going to plug in 0 to these x's, and we're going to get negative 2 over 4, which is the same as negative 1/2. So let's put negative 1 right there, negative 2 right there, so negative 1/2 is right there. So I know that my line's going to go through that point. Actually, I'm not doing a good job right here. It's just getting late. Alright. But I want to confirm that. I want to confirm that this is supposed to be concaving down. And also, I guess it can confirm also if it's supposed to be decreasing. All I need to do is take that 0 right there. And if I want to confirm that this line is supposed to be decreasing, I just need to plug that 0 into this guy. If I plug 0 into this, that would be 0 minus 4. Then I square it, it would be positive 16. We would have a negative 16 divided by positive 16. That would be a negative number, which means if f prime is negative, we should be decreasing. Hey, we're decreasing right here. All right, well, what about the concaving down part? Is that supposed to be concaving down? Let's see. Let's take that 0. We plug it into this guy right here. I plug in 0. I have negative 4. Negative 4 raised to the 3rd power. That would be a negative number. Then I have 64 divided by a negative number. Actually, it's negative 64. And that would give me a negative 1. So I have a negative concavity, which would be a concave down. This line is correct. Now, the other line can either be increasing or it can be decreasing. So I'm just going to plug in this 3 into this guy. Now that's just my choice. You can totally do this a different way. You can check the concavity and base your curve off concavity, because this one is concave down, this one is concave up. So if you take that 3 and plug it into the second derivative and it's concave down, like you get a negative number, then you know it's going to be in the bottom. If it's concave up, then you know it's going to be on the top. That's a nice thing about asymptotes. The curves are attracted to the asymptotes. So if it's attracted to the asymptotes, that means it's going to approach the asymptotes. The curve will bend to appease the asymptotes. Alright, so I'm going to take that 3, plug into this guy, see what we get. See if we get a positive or negative. See, 2 times 3 would be 6, subtract the 4 is going to be 2. Square that, it doesn't matter, that's going to be positive. Negative 16 divided by positive is going to be a negative number, so that means we're decreasing. The curve must be right here. Alright, now I know I didn't use all the tools, but you can get a rough sketch without having to use all the tools. Another thing that you could do is you could try to see where this line is going as it approaches 2. Now that's using limits. So I'm going to write it really quick. It's not one I fancy, but it is another way of doing it. So let me clean this up a little bit, and this will take me about 30 more seconds. So you're going to want to think about 2 different limits. You're going to think about the limit as x approaches 2 from the left side, and the limit as x approaches 2 from the right side. And we're taking the limit of 3x plus 2 and 2x over 2x minus 4. Now this is going to take a little bit of thinking right here. So as we get closer and closer to 2, think about it. You're plugging in 0, you're plugging in 1, then you're plugging in 0.5, then you're plugging in 6, then you're plugging in 0.7, 1.7 and 1.8, 1.9. You're getting closer and closer to 2. What is happening to this? What is this approaching? Now let's look at just this one right here. As we're approaching 2 from the left-hand side, the numerator is always going to be positive. You know, think about that. We're plugging in 1, then we're plugging in 1.5, then we're plugging in 1.6 and 1.7, 1.8. The number that we're plugging in is getting bigger, and that's just making this slightly bigger and this slightly, or then you're adding 2, which increases the number even more. Now the denominator, this one's a little more difficult to think about because we have subtracting by 4. We know that if we plugged in 1 to this, we would get a negative number down here. We get a negative 2. If you plugged in a number greater than 1, that would make 2x a little bit bigger, and then we subtract 4 from it. It's not going to be negative 2 anymore. It's going to be a number that's closer to 0, like negative 1.8 or something like that. And then if I pick a number that's even closer to 2, this number that we would get would be even smaller or even closer to 0. So we're constantly dividing this numerator by smaller and smaller numbers. And not only that, we're dividing them by negatives. So that means we're always going to get a negative number. And because we're dividing this by a smaller and smaller number, that number is getting bigger and bigger and bigger. So we're approaching infinity, but don't forget, they're negative because the top is always positive and the bottom is always going to be negative. Alright, so what about this guy? Well, the same scenario is going to happen. The top is always positive. And the bottom, if we're greater than 2, that means if I multiply this number, this 2, by a number greater than 2, then that number is always going to be bigger than 4. So if I subtract 4 from it, then that means we're going to just get a small number that's going to stay positive. Now, as we get closer and closer to 2, we're going to keep getting a smaller and smaller number on the bottom, which means if we have a number up here that's always positive and we're dividing it by a smaller and smaller number, we're going to be approaching infinity. And that information right there would tell you that, oh, as I'm approaching the vertical asymptote, I'm going to be going down, and this side, as I'm approaching the vertical asymptote, I'm going to be going up. Now, honestly, I don't like this that much, but it is a tool that you can use, and I wanted to talk about it for a minute.